These are the AP exam practice questions for our Chapter 14 review. So let's take a look at them. The first question here, number 16, says a sample of N2O5 was placed in an evacuated container and the reaction represented above occurred. So we see N2O5 decomposing into two products, NO2 and oxygen. The value of PNO2, this is the pressure of your reactant, was measured, and the partial pressure was measured during the reaction and recorded in a table. So what we're doing is we're showing the pressure of N2O5 as the reaction runs here, and then we've been given the natural log of N2O5 and the inverse of N2O5. Now remember, what we did is we graphed these, so we made a graph. So for example, for the first one we did time versus just the pressure, and then we saw the curve, then we did the ln of pressure, and we got another curve, or we got a straight line, and so forth. So that's essentially what they're referring to here. So they want you to graph, and recall that if you get a straight line, that is when you can figure out what type of order it is. Now if you get a straight line, in the case of just the pressure without doing anything to it, you got yourself a zero order reaction, because as the reaction proceeds, the rate does not change, which means the concentration is not affecting the rate. And what we did is we said essentially just memorized that if it's a straight line to begin with, it's zero order. If the natural log gives you a straight line, it's first order. If the inverse gives you a straight line, it's second order. And if none of them give you a straight line, it may be third order, and so forth. So the question here is, which one of these will give us a straight line? Now we can try to graph them, but this is a quick question meant to be answered without graphing. Essentially what we're going to look for is which of these produce a straight line. Now in order to produce a straight line, the ratio of time and the change here should be the same, which means as you go through the reaction, the change should be the same, and that's how you get a straight line. Remember, a straight line means you have a slope, a constant slope, which means the rise over run is the same throughout the reaction if it's a straight line. So looking here, I see that in my time interval I'm always increasing by 100 here, 100 here, and then 100 here. So I'm going to look for which one of these also is constant as you increase it. And looking at it here, we're increasing by 75. Now here we're not increasing by 70, or decreasing by 75 rather. Here we're not decreasing by 75. Here looks like decreasing by less, quite a bit less. Here's we're decreasing by more, even less, 19. So this can't be it. However, if you take a look here, we're decreasing by 0.7. And then from here to here, it's 0.7 if you subtract the two numbers. And from here to here, it's 0.7. So we found it. We see that the ln versus time gives us a straight line, because it's the same every single time here. And so that will give us a constant slope, and that is the one we pick. So it indeed is a first order reaction. So again, just memorize what makes a first, second, and third from the graph, and then pick the one that's constant. Number 17 says the reaction represented above occurs in a single step that involves a collision between a particle of NO and a particle of NO3. So here's the reaction. You'll notice that the rate law contains both reactants in it, which means that the mechanism has both of these reacting together. That's why they appear in the rate law. So it's an NO particle must collide with an NO3 particle in order for this reaction to occur. That's what the rate law is showing us. Remember that the mechanism could be a number of different things. It could have been just NO reacting by itself. It could have been two NO3s reacting by themselves. But the rate law tells us that both of these are involved directly in the collision. And that's what the scientist says. Here it says the scientist correctly calculates the rate of collision between these two that have sufficient energy to overcome the activation energy. The observed reaction rate is only a small fraction of the calculated collision rate. Which of the following best explains the discrepancy? So remember, the activation energy is how much energy these must collide with into each other in order to react. And what was observed is that the rate is not as fast as the collision frequency. So these guys are colliding very often with each other. So here they go, colliding with each other. But they're not producing a reaction every single time. And we're asking why. Now if you read through these possibilities, the correct answer is B. And let's kind of go backwards. Let's explain why B is the correct answer and then why the others are not. Here it says the two reactant particles must collide with a particular orientation in order to react. This is true. Just combining together doesn't help unless you're oriented. Maybe this active site must react with this active site. And so if they're not oriented properly, the reaction would not occur. So that's essentially one of the requirements of the collision theory for them to react. And that's really what they're trying for you to see. A says why it's not true. The energy of collisions between two reactant particles is frequently absorbed by collisions with a third particle. We don't know of a third particle. The rate law actually says that there's only these two particles. So that's why that one's wrong. The activation energy for C says for reaction is dependent on the concentration of the reactants. This is not true. The activation energy is simply how much energy the particles need to get. Remember, this is the activation energy. And the more you have, the more particles can scale that activation barrier, but that doesn't change. The activation energy doesn't change just because you have more particles. It also doesn't change just because the temperature is increased. This is also wrong. Increasing the temperature allows more particles essentially to scale this barrier, but the activation energy stays the same. So think through those, and hopefully those make sense. Let's take a look at some more. Take a look at 18 here. A kinetics experiment is set up to collect gas that is generated when a sample of chalk, consisting primarily of solid calcium carbonate, this is what chalk is made from, is added to a solution of ethanoic acid. Now, what we'll have is we'll have an acid reacting with a carbonate, and in this case, anytime this happens, CO2 gas is released. So if you ever put, this is actually the same thing that happens when you put soda, baking soda, against vinegar. This actually is vinegar. You get CO2 gas. The rate of the reaction between these two is determined by measuring the volume of gas generated at 25 degrees Celsius. So gas would be this guy here as a function of time. We don't really care about the exact reaction itself. We're not going to write that out. We're just asking which of the following experimental conditions is most likely to increase the rate of gas production. We just know that these two are our reactants. Okay, A says decrease in the volume of ethanoic acid solution used in the experiment. Now remember that we said increasing the reactant concentrations increases the rate. So if we decrease how much we're putting of the reactant, this will not increase the rate. This one's out. B says decrease in the concentration of the ethanoic acid. This is the same thing. If you decrease how much reactants you have, you'll actually decrease the rate. C says decrease in the temperature at which the experiment is performed. Temperature has a positive effect. Increasing the temperature increases the rate. So decreasing it will actually decrease the rate again. And D must be correct because it says decreasing the particle size of the calcium carbonate by grinding it into a fine powder. This is true. Calcium carbonate, say a piece of chalk here, that looks like a chalk. If you throw it into some acid, it will begin to react. Bubbles will begin to start forming. It'll begin to react, but not as fast as if you break it into pieces or if you grind it into a powder. This is because the surface area will be increased. When it's in a chalk form, the acid can only attack the outside of it. So the reaction rate isn't as quick because it doesn't have access to as much of the solid as if you were to grind it. If you grind it and now it's a powder, say sitting at the bottom here, now the acid can much more quickly attack it. In a sense, it can attack it from the inside now because the inside has been exposed. So this is kind of an indirect way of increasing the concentration of your calcium carbonate, one of your reactants, which increases the reaction rate. So D is the correct answer. All right, let's take a look at number 19. Number 19 says a reaction and its experimentally determined rate law are represented above. Here we have two reactants combining into a product. The rate law is given to us on the right. We notice that the rate law contains only one of the reactants. in itself. So a chemist proposes two different possible mechanisms for the reaction, which are given below. And essentially we're asked which mechanism is consistent with the rate law. So remember, the rate law allows us to see inside of the mechanism. And a chemist can propose how this reaction runs, and then we can evaluate it. Now, I'm going to quickly skip down to the answer again. What you see is that the slow step of the reaction in both cases contains X2 as the reactant, which tells us that both of these mechanisms could work. Remember, the slow step is the one that appears in the rate law, because the rate of the reaction cannot go any faster than the slowest step. The slow step actually limits how fast the whole thing goes. So the reactants that appear in the slow step appear in the rate law. Now the rest of it, as long as the rest of it matches, and the rest of it should, if you collapse the whole equation, you should get back this original equation, which you will in both these cases. So they're both valid, and both of these are consistent with the rate law. So C is the correct answer. And essentially that's because the slow step contains just X2 in both of them, which is the same as the rate law. So this is a much simpler one than it looks from the onset. Okay, and let's do the last two here. Here we have a similar equation. The equation represented above for the decomposition of a compound. So we have a compound decomposing in two elements. The diagram below shows the two reaction profiles, path 1 and path 2 for the decomposition. So notice we have these two paths. Remember that this here is the activation energy. We just talked about this in the previous. This is the activation energy. And we're asked which of the following is most likely accounts for the difference between reaction path 1 and reaction path 2. So taking a look at these, A says a higher temperature in path 1. Now, temperature here is not represented. The activation energy is simply how much energy the particles must attain in order to go from reactants. Remember, this is reactants, and this side is products. This just shows how much energy is required, but the temperature here is not represented. So the temperature is not higher in either one of these. The temperature is how much energy a reactant particle needs to get to the top of the hill here so it becomes a product. So it's the presence of the catalyst, and the key thing here is that the catalyst is the one that changes the activation energy. This is kind of truth. Catalyst changes activation energy. That is what you want to remember for the test. So the presence of a catalyst in one of these paths. The catalyst always lowers the activation energy. It changes by lowers. Really, we should say lowers. So reaction path 2 shows a lower activation energy, which means it is the correct answer. 21 then says, which of the following best describes the flow of heat? Now, we see that our reactants start out at a lower energy. Products end up at a higher energy. So this means as the reaction runs, energy has been gained by the reaction. So if energy has been gained, that means it's an endothermic reaction. Energy has been absorbed from the surroundings into the reaction. And the change here is actually 50 kilojoules. So here it says 50 kilojoules of heat is transferred from the surroundings into the reaction. B then would be the correct one. From the surroundings into the reaction. And again, the reason for this is we see essentially a reaction coordinate diagram shows you two energy changes. It shows you the activation energy change, and then it shows you the overall energy change. The first one is called the energy of activation, usually E sub A. The second one is your delta H. And delta H here is positive because you end up at a higher energy than you began with. So if you do a higher number minus a lower number, that's how you get a positive delta H. Now a negative delta H incidentally would look like this. So here, this still is your activation energy, and then your delta H would be this change between here and the starting. Okay, so think through these, look over them, make sure they make sense. These are tougher questions, but very representative of what will be asked on the test. So this completes for us the review of the Chapter 14 test.